So welcome back everyone. Our next speaker is Marco Zambon from KU Leuven, and he's going to talk about singular subalgebroids and their integration. Please.
Thank you very much. So let me see if I can just work. Okay, there's a laser pointer. Okay, so well, thank you very much. Thank you to the organizers, Francesco and Pauli, for organizing this event. Also, thank you to the chairs and currently online. So this talk builds in part on many other talks in the course by Christian, in the sense that many notions that appear here would have appeared there too, but it's in a slightly different setting. So this is work that I did with my collaborator Jakobs Trulidakis, and that finally is in the archive, even though maybe not in really final form. Okay, so what is this about? Well, this is about differentiation and integration, like in Poisson talk. So everyone knows that if you have a Lie group, you can associate with the Lie algebra as some kind of differentiation procedure. In one course, they convert the inverse operation integration. So the integration of the Lie algebra is some Lie group with the property that the algebra is a given one. And what I will address is, something similar for other infinitesimal objects that I call singular subalgebroids. So what is their integration? And roughly speaking, the answer that we give will be differential groupoids with some structure. So let's show a special case of this. Well, a non-special case. So this goes back to the work of Wolfgang and Poisson. So the setup is we have a Lie algebroid, and let's assume every time I write Lie algebroid A, it will be integrable. That's an assumption. To simplify things, so let's fix and integrate in groupoid. And let's look at wide Lie subalgebroids. So wide means that B is a subbundle of A over the whole base M. That's what it means. And in this theorem, gives you a notion of integration. So what should we call integrals? Well, according to modern conversion, not just a Lie groupoid integrating B with its induced algebra structure, but you don't want to forget the fact that B sits inside A. So you also want to have a morphism of Lie groupoids to G, which integrates the inclusion of B into A. And then this theorem tells you, how many such things there are. Because it tells you that there is a special Lie groupoid integrating B, called H minimal here, that comes with a morphism to G integrating inclusion, and any other is basically a cover of it. Well, it has a surjective map differentiating the identity at the level of the algebroids. So this diagram commutes. So there is a smaller one, and all others are kind of colors. Okay, so this was well known. Okay, so now I will say a word about the objects that what I want to integrate. So the singular subalgebroids. I will say something about what we claim are a good notion of integration, namely these diffeological groupoids with extra structure, and then I will talk about differentiation and integration, giving some examples. Okay, so singular subalgebroids. It's just a name for what? For so given a Lie algebroid A, we look at a family of sections, so closed under multiplication by functions, so a submodule of the, say, compactly supported sections of A. And you require that it's involutive, so closed with respect to the Lie bracket of sections of A, and that is locally finitely generated as a module. So if you saw the definition of singular foliation in Alfonso's talk, this is a slight generalization, but the conditions are exactly the same. So before I give examples, a couple of remarks. One is that this is a relative notion. Relative in the sense that, so I'm not saying I'm looking at some C-infinity module of, of something. I'm saying this has to be a submodule of the sections compactly supported of a certain Lie algebroid. And so in this, what I'm going to say now, differs, for example, from the setting of Poisson's talk. And like the intrinsic structure that such a submodule inherits is the one of the Lie algebra, well, as in stock, but well, we still have an ambient Lie algebroid around, and so this is quite a geometric kind of Lie algebra. So two main examples. When A is the tangent bundle, which is the algebroid, as we know, this recovers exactly singular foliations, as in the top right hand. So a bunch of vector fields satisfying algebroids. And so these objects are called singular because, well, they generalize something that is certainly regular, constant rank, named widely subalgebroids. So if we have a widely subalgebroid and we take all these complex part sections, then well, we get one of these objects here. So this is the regular case. And so I will maybe quickly show that there are also other examples that are interesting. So one quite general class of examples is the following. If you have a Lie algebroid morphism covering the identity, for example, the anchor of your Lie algebroid E, then, well, the image of this Lie algebroid morphism might be something ugly, right? So the vector bundle map usually jumps rank, doesn't have constant rank. And but you can take the map, the vector bundle map at the level of, well, you can take the map at the level of sections. So this covers the identity, so there's no problem. And you can take the image of that. That is the singular subalgebroid of A. So a special case, so this is the hierarchy of things. A special case are so-called projective singular subalgebroids, namely those which as modules are given by sections of some vector bundle, some abstract vector bundle. That vector bundle is not necessarily a subbundle of A. But it comes with a morphism to A, which is injected almost at every point. And the even more special case is when these are widely subalgebroids, in which case the vector bundle sits inside the sketch, the relation between these things. Okay, so the main thing to remember, I guess, is that I'm dealing with a relative notion, relative to an ambient algebroid. Okay, now diffeological groupoids. So I will say yes. So what the challenge in this business, or one of the hard things, was to single out some properties that our integrating objects should have. And so it's a candidate for integrating object is a diffeological groupoid, and we say briefly why. But the main question was what extra properties or structure should you ask in order to recover singular subalgebroid. And okay, so by diffeological groupoid, I mean one that lives over a manifold. So I want the space of units to be a manifold. So this is already more special with respect to the other talks we saw about diffeological groupoids and Kristen's mini course. Okay, so this is so I wanted to present this lemma because it's quite general. So so maybe it's useful as an aesthetics. So let's try to go through it slowly. So I have a diffeological groupoid. So what is the diffeology? In particular, I can fix a generating set of plots. So a bunch of plots, so smooth maps, so to say, from open subsets of Euclidean space into H, which is, well, in the obvious sense, generate the whole diffeology. And the statement is essentially that nearby points of the units in H, there are nice plots in the generating set. And I will show a picture in the next slide. So nice means that in the domain of the plot, so I will always denote the domain by O and then the name of the plot. Then we have a submanifold such that the plot restricted to there is a diffeomorphism onto a neighborhood in the space of units. And furthermore, if you look, so you don't know much about the source and target maps of the diffeological groupoid. So source and target maps are what Christian called N and R. And you don't know much about them, but well, if you look at them under this plot, then they're submersions. And so these maps are defined on the domain of the plot and go into M, so the maps with manifolds, but it's the motions. So this is a picture, and so this is the domain of the plot. I have a nice well, there exists a submanifold there such that the restriction of the plot is mapped diffeomorphically onto an open subset of the space of units, which is this horizontal line. And so these plots are nice, but they might not know much about the diffeological groupoid in the neighborhood of the units. So for instance, the image of the plot might not be open, as I try to draw here, might not be an open subset of H with its one-dimensional topology. Okay, so one property that I will enforce later on, but I want to introduce already now, is the following. So something you can ask about a diffeological groupoid, namely that there exists a generating set of the diffeology consisting of open maps. So open maps are maps that map open subsets into open subsets. And the nice consequences of this are that through every point of your diffeological groupoid, you have a local bisection. So existence of local bisections. And this in turn implies that the source and target maps are local subductions. So already, well, this term was already pronounced today. These are analogs, well, according to some people at least, of submersions in the diffeological category. And these things in particular are open maps. So exactly as a Lie groupoid has the property that source and target maps are submersions, well, it might be nice to have analog properties for a class of diffeological groupoids, but this assures these properties. Okay, so now I'm switching setting a little bit. So I will take a singular subalgebroid. And well, the essence of the next few slides is that you can associate to it in a canonical way a diffeological groupoid. So yeah, so you know that if you have an integrable algebroid, there is a special integrating Lie groupoid, for instance, like the source connected one. Something similar is going on here for singular subalgebroids. And I will explain some properties of this diffeological groupoid that will be associated to B. And yes, but they're nice geometrically to give some intuition, but they're not strictly necessary to understand the rest of the talk. So maybe here I will go a bit faster. Okay, the setting, we have a Lie algebroid, integrating Lie groupoid, and I take a singular subalgebroid. The statement is there exists, well, a canonical diffeological groupoid over M, which furthermore comes with a morphism into your fixed group. And so morally speaking, this object integrates the singular subalgebroid, and this morphism integrates the inclusion of these intersections. So here I'm saying what this specializes to. Well, this is a very rigorous statements. If my curly B is sections of a wide subalgebroid, this recovers exactly the construction of Murdyke and Merchun, the one I presented in the second slide. And when B is a singular foliation and as Lie groupoid, you take the pair groupoid, so the smaller possible one. This recovers the construction by Andrew-Dakis and Scandalis, which is the same one that Alfonso talked about this morning, and which, say, in the case of irregular foliation, recovers what is known as holonomy groupoid. So maybe to give a word of motivation, so if a regular foliation on a manifold is, well, it's certainly an equivalence relation, right? You're taking your manifold and you're partitioning it. Well, you're defining a partition, which has some smoothness properties. However, the smoothness properties are not really wonderful in the sense that if you look at the equivalence relation itself, which is a subset of the product manifold cross manifold, what you get is not a submanifold, not even any more submanifold usually. And the holonomy groupoid is some groupoid that one associates to this. to the foliation, which replaces, in a sense, the equivalence relation and has the property that is always small. So it's the smallest replacement for the equivalence relation. Okay. So so this object will also be called Holonomy groupoid, but we'll always say of B because that's what it is associated to. And it depends on the choice of Lie group. Sorry, Lie groupoid integrating A. Okay, so a word on the construction. So without getting too technical. So out of the singular subalgebroid, somehow, I mean, one can construct certain smooth manifolds with smooth maps to G. And this data somehow encode and desingularize the singular subalgebroid. I'm not going to tell you the exact axioms. The holonomic groupoid is given by the disjoint union of these things divided by some equivalence relation. And so this already tells you that the holonomic groupoid has an induced diffeology.
So what is U again? Sorry.
So U is a manifold. I mean,
how do you get it? Just roughly. I mean, you said you don't want to say it, but understand it.
So you can take local generators of your singular subalgebroid. So say for singular foliation, that means you take a finite number of vector fields that generate the foliation locally, and you take the trivial vector bundle whose rank is the number of generators. Mm-hmm. That's an example.
But so, there's only one U, or the many as such use.
No, the many. That's why it index.
But above is only one. So what is this U above?
So depending on choices you might want to make, you will get a certain U. So if you choose a set of generators, you get U as I told you.
But locally.
Yes, only locally, and you get also the map.
Does this U is local?
Yeah. So they're local. But, I mean, I'm taking care of disjoint union. So the point I want to make is that each of these UIs is a manifold, possibly of varying dimension if you vary I, but it doesn't matter. So the disjoint union of manifold is not a manifold, but it's still a diffeological space. And as Christian said, quotients of diffeological spaces are again diffeological spaces. So there is a clear diffeology here, and one then maps to G just in this case here. Mm-hmm. So this thing is a diffeological groupoid, and actually working a bit, one can show that that it satisfies the open map property I explained earlier. So meaning that so the plots which are exactly these maps here, they are open maps. Okay, and so the reason why I'm mentioning this holonomic groupoid is that it will provide an integration of B, as we will see later. So if you want to have an example of integration in mind, well, this is one. Okay, these objects are interesting also because you can associate system algebra to them. So there's motivation for people working in non-competitive geometry, and it has some smoothness properties in the usual sense. For example, the restrictions to leaves are Lie groupoids. Okay, so that's all I wanted to say about the groupoid. And as said, the rest of the talk does not really depend on this, but I wanted to. I forgot the slide where I can give a couple of examples. So for a certain singular foliation, all vector fields vanishing at the origin of the plane, you get this thing here, theoretically. So notice that so this is the fiber over the origin. So over the origin, the fiber of this holonomic groupoid is 4-dimensional. It's real 2. Over other points, it's only 2-dimensional. So this makes it clear that it's not, it cannot possibly be a groupoid. And okay, maybe I will just leave it here for you to read. So the last example is basically saying that you can construct it in a very explicit way for singular subalgebroids arising from the algebraic morphisms. So there are explicit constructions. So let me see.
What is K?
So here I'm taking the algebraic morphism or the identity, and then a morphism of Lie groupoids that integrate it. So K is a Lie groupoid integrating E.
That you assume.
Yes. That's why I say that.
Yeah.
Yes, Yes, I assume that. Well, of course, if you take K to be sourceably connected, then it will have the property that it has a morphism to G, integrating the morphism of the algebroids. And then we take some quotient of it, which will make it, the result will be highly non-smooth usually, and well, it's explicit as a saturated component at least. Okay. So I started at sorry?
Around quarter past you started, right?
Yes, but I think I have 1 hour.
Yeah. Oh, okay, yeah. So almost like
Yes. Okay, so I'm going much faster than I wanted. Sorry. So we'll slow down.
But it's really very fast. Partially, it's you just say read it more or less, right? Is that like the last line you can explain? For example, I mean, I would appreciate if you explain it.
Okay, I can do it in 2 minutes. Okay, so let's see. I have a morphism of the algebroids of an identity, and I'm interested at the image of this one meant in terms of sections. Okay, so what can you do? You can integrate this algebraic morphism to a Lie groupoid morphism. Right, so you get this nice groupoid K. Well, and the statement is that the holonomic groupoid will be a quotient. Now, quotient by what? I have to tell you. So it will be quotient by a normal subgroupoid, and that normal subgroupoid is this. So these are all elements of K. Well, okay, these are elements of K. In particular, these elements of K will lie inside the isotropy groups of the groupoid. So if you see, if I pick an element in this I, its image under the source map will be equal to its image under the target map. So in the isotropy groups. But so this I is not the union of the isotropy groups, it's smaller. So what I'm asking is that, so I'm taking only the points in the isotropy groups with the property that they have a local bisection through them, which lies with a property that after you apply the morphism, you end up in the identity section of G.
So that's a smoothness condition or something, right?
It singles out, yeah, it's a smoothness condition. So let me draw a picture maybe. But I prefer not to explain it too much. Also because it's more of an analogy, just not to come up with a concrete example.
Would you write up there?
Yep.
I like side. He means that you should maybe
The side way.
No, right where you want. So now you need to try it first, maybe. Does this drawing device?
Oh, it's okay.
Okay.
So I only want to make one drawing. So actually, this is just an analogy. I'm not giving a concrete example. So take a vector bundle over R cross M, and take some kind of singular subbundle, singular vector subbundle. So at most points, I take just a zero vector space. At some special point, I take the whole fiber, and only here. Yeah. And so this could be, let me see if I next to it. So this, for example, so there exists a vector bundle morphism from this to itself, whose kernel looks like this.
So sorry, fiber is just R? Or is more?
R.
Okay, so there's some of them where you have all of R and some where just points in the subspace.
So in white, I drew the vector bundle R cross M. And then I'm taking some kind of singular subbundle in there. That's what I draw.
But mostly there are zero sections, or mostly there are these lines?
Mostly there is zero section. Only at this point,
okay,
the fiber is one-dimensional. And so this kind of singular subbundle can be realized. So this very one can be realized as the kernel of a certain vector bundle morphism. So kernels look like this. Okay. So this is the analog of the union of the isotropy subgroups. So making just an analogy here. So the analog of what I call I in the slide is given by the points here, which admits an extension to a section of my vector bundle, which lies inside this subbundle. So each of these points does the job. 0 here also does the job. You take the zero section. But if I take this point here, any little section through that point will not lie inside the right. That's it. Thank you. So now I'll talk a bit about differentiation. Well, differentiation first, because, well, integrations should be kind of the opposite of operation, right? So first we have to understand differentiation. And okay, so my aim, so before I show any slide, so what's the aim here? Given a diffeological groupoid, well, I would like to associate to it a singular subalgebroid. So like philosophically, this is similar to what Christian addressed in this course, but we're in a slightly different setting. And so I need properties. Let me show you one property. And I don't have a drawing for this. And so this is a property for diffeological groupoids. So this is again something relatively general. So you might like this property or not, but it's something about diffeological groupoids in general. And so before you read this, like the essence is, this is saying that nearby the identity section, well, the nice plots that I presented in the first lemma, so those for which the restriction to certain submanifold is diffeomorphism to a subset of identities, they are unique in some sense. So some kind of uniqueness statement. So I'll try to spell it out, but I agree that it's a bit ugly to read. So the property, which we call Holonomy-like, it's just a name, is the following: that there is a generating set of plots for the diffeology of H, but only in a neighborhood of the identity section. That's enough. With this property. So if you take any two plots in this generating set, and I drew them here, chi and chi prime, and they are nice plots, such as in the lemma that I presented earlier, which means that they map certain submanifolds here diffeomorphically onto an open subset of the space of limits. And moreover, the image agrees. So the image of psi restricted to the first submanifold and psi prime to the second one, they agree. Then necessarily there is a smooth map between the domains of the plots that make the diagram commute. So in terms of diffeologies, so this means that that chi is kind of redundant because you can obtain chi prime is redundant because you can obtain chi prime as a composition of your plot chi and a smooth map between open subsets of I. So uniqueness is not really a precise term, but it's, you can recover one of these two plots using the other, and vice versa. Okay. So by the way, so I was thinking about this elastic diffeological groupoids that Christian mentioned. So this property that might look quite artificial. So I believe this assures that at points of M, you have this elastic diffeological space property. So but the property you mentioned is, if I understood correctly, essentially a property about being able to bring everything back to just one plot, and that's it. Okay, so what I will say later what this is good for, and okay, so now I'll try to explain what I mean by differentiation. So this is a relatively naive idea. So the starting point is a diffeological groupoid with a morphism covering the identity to my fixed groupoid. So I remind you that I'm working some kind of relative setting. So sub-objects of say the algebroids. And so here I don't just want the diffeological groupoid, but I want the map. Okay, so out of this data, how would you get a bunch of sections of the algebroid of G? And yes, well, H does not have a algebroid.
So, Marco, there's a question or a remark by Joel. It will probably imply everywhere then via translation by bisections.
What? Imply what?
I mean the elasticity property.
Well, you first have to assure that to every point you have a bisection.
Okay, you don't have that for these.
In general, I don't think you have it. Once you have it, I agree with what you said. So, okay, let's try to deny it. So I want a bunch of sections of the algebroid on this side here. Well, H does not have a algebroid, so I cannot start from that. But sections, well, I can think of sections of the algebroids as velocities of paths of bisections. A bit like you can think of the tangent vector as the velocity of a path in the manifold. That's what I try to draw here. So this beta gammas, so I is an interval b lambda, sorry, is a smooth family of bisections of my diffeological groupoid. So here I drew two of these bisections. At time 0 they go through the identity bisection. So I can take d lambda at time 0. So if I fix the point of M through this as a very lambda, I get a path in the fiber, in the source fiber, and then I can just take the velocity. I get an element of the algebroid. So forget that was wrong. But so I can take I can look at all this bisection b lambda. Then I can apply the map to my Lie groupoid. So then I will have a family, one parameter family of bisections of my Lie groupoid G.
But they are local.
No, global.
Because this was a wide subgroup. No, H is not a subgroup.
So here, well, they're global.
In G.
Well, these B lambdas are bisections in H. After I apply the morphism, I get bisections in G. Yes. So these here on the right are a family of bisections in G. There's a time 0 go through the identity section. And well, d lambda times 0 of that gives me a section of the algebroid of G. And okay, so and I need the diffeological H to make sense of this adjective here, smooth. I want a smooth family of bisections in H, so that after I apply this map, I get a smooth family, smoothly varying with lambda of bisections on the other side, and d lambda makes sense. And okay, so yeah, so philosophically, I think this is saying, okay, I cannot take like velocities of paths of bisections, for instance, on this side, but I can do it on the other side because I have my morphism to a different point. And so one condition that well, I will impose in a second, and that it's not very nice, I agree, or seems very strong, is this, which is saying that if you look at the same set of sections of the algebroid of G, where you replace the word family, smooth family, with smooth one parameter group. So if you enforce the property that b lambda multiplied with b eta is b at times, so to say lambda plus eta, then I want to get the same set of sections. So one result, one result is the following. So this procedure, sorry, go back one second. So this procedure that out of this data gives you a bunch of sections of the Lie algebroid and the only Lie algebroid around one of G, and automatically actually gives you a submodule. So that gives you a singular subalgebroid if some extra conditions are satisfied, namely this Holonomy-like condition that I presented a couple of slides ago, and the condition on one parameter groups of the previous slide. And okay, so right, so and I want, well, at this stage at least I want to impose these conditions because out of my data, so the Diffeological groupoid with a map to G, I want to obtain a singular subalgebroid, not just a random module of sections. And to explain a bit what the conditions are needed for, the first condition needed to get that S is locally finitely generated, the second condition to get evolutivity, but maybe we can replace the second condition by one that looks weaker. So this condition on velocity, on closeness of S of this module with respect to derivatives, with respect to lambda, that also ensures evolutivity. And so this is well, maybe working a bit more, I can do without this condition here. But at this stage, yeah, I cannot say anything more. Okay, so this was differentiation, how to get a singular subalgebroid out of the Diffeological groupoid with a map to G. And okay, so what should integration be? Well, integration should be the opposite process, the inverse process of differentiation, right? So one possible definition would be, okay, I say that, well, one possible definition could be, given a singular subalgebroid, I call integration a Diffeological groupoid with a map to G, such that this is satisfied, and the module I get is exactly the singular subalgebroid I started with. But actually, I would like to impose more conditions to make it so that I get less integrations, and hopefully in this way one can get a better hold on what the integrations are. Right? The more conditions you impose, the less objects you get, and the conditions that we impose are satisfied by all the examples we want. So for the moment there is no harm in imposing these conditions. So the starting data is as in the previous slides, the Diffeological groupoid with a map to the groupoid over the identity. Now I take a singular subalgebroid, and so what should be the integrating objects? So I call them integral instead of integrations, but it's just a matter of language. So the integrals should be, well, Diffeological groupoids with a morphism, with the property that they differentiate to be in the sense of the previous slide. So this is sort of expected. And then I will add two more conditions. One is that the Diffeology is generated by open maps. That's the very first property that I showed in one of the first slides. So that's the property of the Diffeological groupoid H alone. And also I want this morphism to be kind of injective. I will say what it means now. And well, why? Because I don't want. I want the Diffeological groupoid to be roughly of the same size as the singular subalgebroid is supposed to integrate. So I don't want it to be unnecessarily big. So the precise definition of almost injective is that if you take a local bisection, so we're looking at this map here. If I take a local bisection of H, my Diffeological groupoid, nearby the space of units, and it maps to the identity bisection of G, or inside the identity bisection of G, then my bisection itself must be an identity bisection. So that's almost injectivity. And so the second condition on the Diffeology being generated by open maps Well, it's there for several reasons. One reason is that thanks to this condition, the third one makes, well, it's a meaningful requirement. So the second condition implies that through every point we have a local bisection, and the third condition is a condition of local bisections, so it will be kind of empty if there were very, very few local bisections to assure that we have lots of local bisections. So that's one reason, but it's not the main one actually. I will mention the main one. So now until then, I will just show examples. I think I can go back slow. So at the beginning of the talk, I said that given a singular subalgebroid, you can associate with canonically a groupoid, which is one of our diffeological groupoid. That was what I called Holonomy groupoid after the construction of Integrability Scandalis. And that came with a map to G. Well, this is an integral. So this is like the prototypical example of integral. So the canonical object you can associate integrates your B. So that's good news. So now I will discuss a variation of this notion, which we don't want to be an integral for reasons I will try to explain, and which indeed is not an integral. So let me try to explain something orally first. So let's go back to regular foliations. So you have your manifold, it's partitioned by this submanifolds of the same dimension. So as I said, if you view this, the foliation as an equivalence relation, it's not a submanifold. So the equivalence relation, it's on the manifold cross itself, and you say, you say 2 points are in the same equivalence class if they lie in the same leaf, and so on the product of the manifold times itself, you draw the points consisting of pairs of points lying in the same leaf. So this is a subset of the product. So that is not a submanifold. That is not smooth, and so that is not an object that you want to call an integration of the involutive distribution associated with foliation. So you don't want that. It's not even smooth in the usual setting of differential geometry. And so I want to exclude that. That's what I'm saying here. So the name I give to this thing in general is graph of my singular subalgebroid. So it's just an image of the groupoid morphism into G. So the case of foliations I just mentioned is the one where G is equal to the pair groupoid. So the image in that case is a subgroupoid of the pair groupoid in the constellation. But we can do this more in general. So the image is itself a diffeological groupoid. With what diffeology? Well, we saw that quotients of diffeological spaces are again diffeological spaces. So images of maps are in particular quotients. Right? So they become they have a diffeology. Okay. So this diffeological space, the subgroupoid of G, is not an integral. And it satisfies almost all the assumptions in my definition, except for the fact that the diffeology is not generated by open maps. So that's maybe we'll go back. So go back here. So that's the reason, the main reason why I want this condition to throws this out. And okay, and this is when we formulate the example of the regular or also smaller foliation. Okay, so now more well-known maybe examples. So okay, to be a bit explicit. So an example. So to talk about singular, if I want to specify a singular subalgebroid, I first need to say what is the ambient algebroid. So let's take a Lie algebra as ambient Lie algebroid, then a singular subalgebroid is just a Lie subalgebra. That's what I call K here. So I can try to apply well, so I'm talking to apply this definition to that special case and say, and I can try to say what are all integrals in this sense. Well, the answer, luckily, is all integrals are smooth. So the integrals in principle are diffeological groupoids, well, with a map to G. Well, they are all Lie groups. They're all Lie. They're not just diffeological. And to be more precise, they're exactly, you get them as follow. So given the Lie subalgebra K, you know that, well, there exists a unique Lie subgroup of G connected, Lie subgroup of G having this as the algebra. And we take all the groups covering that. So these are exactly the integrations, sorry, the integrals in the sense of the definition I gave a couple of pages ago, slides ago. So for this very simple case, we can say what all the integrations are. And well, the proof uses one effect that I found in a paper by Suryo. So if you have a Lie group, well, in particular, it's a manifold, so it's a diffeological space, right? And so the diffeology is the smallest one that contain, for which the one parameter groups are small, are plots, I should say, are plots, and so that the group multiplication inverse. Okay, so what is this slide saying? At least to me, that well, this definition of integrals that I gave, well, it's reasonable, at least if you restrict to this special case. So it doesn't give you something crazy. And also it tells you that, well, it's in some cases at least it's computable. You can compute what integrals are. Okay, slightly more general, widely subalgebroids. So for instance, if you wanted, you could take A to be the tangent bundle of a manifold, and B would then be a volatile distribution, which, as you know, gives a distribution. Okay. So the statement of the proof is that, so we couldn't make a list of all integrals in the sense of the definition, but at least we could for the smooth integrals. So I said the integrals are diffeological groupoids, but sometimes they happen to be Lie groupoids. So for those, we can say what they are. Namely, they are so Lie groupoids H when integrating B, which have a morphism of Lie groupoids into G integrating inclusion. So in other words, the integrations of the widely subalgebroid in the sense of Mordag-Morchun that I showed in one of the first slides. But we don't know, or at least I don't know, if maybe there exists some integral of my singular subalgebroid that is not smooth. So when in the case of the subalgebras, I could say that it's not the case.
Not smooth, you mean not coming from sections or vector bundle?
No, I mean not a Lie group. No, sorry, not a Lie groupoid.
Yeah.
Sorry?
Yeah, but they're not the manifold. Maybe they're not the bisections in the manifold.
So I'm not talking about bisections, right? So
you talk about the diffeological groups, right?
Yes, yeah.
Groupoids, and they may not be manifold.
Exactly. So on a diffeological groupoid, there is if there is a manifold structure on the what Christian called G1 and I called H, like on the space of errors, and on the space of units, which I assume anyway, so that you get a Lie groupoid, then that smooth structure is unique. So it makes sense. So the statement, this diffeological groupoid is not a Lie groupoid, it makes sense. It's a well-defined statement. So now I will go slightly more general. So we'll take projectively subalgebroids. That's what written up here, and that's not visible. And okay, so and one motivation to look at them is that, well, it's not too hard to show statement that a singular subalgebroid admits an integral that is a smooth Lie groupoid if and only if it is projective. So I recall maybe what projective meant. It meant that this submodule, so this as a single term submodule, is isomorphic to sections of some abstract vector bundle. And that abstract vector bundle then becomes the algebroid as my structure. Okay. Here again, we can make a statement only about smooth integrals.
And does it mean it's a finite rank vector bundle or necessarily?
Yes, sure, yes. Because in the definition of singular subalgebroid, I impose that this is locally finitely generated module. That means that if my module is sections of a vector bundle, that vector bundle is finite rank.
And if it's globally not finitely generated, then doesn't it need a smooth integral?
But it does. So I'm imposing on B that it's locally finitely generated, but I'm not imposing that it's globally finitely generated.
But projective means that or not? If it's a section of a finite rank vector bundle, it is.
I agree. Yes.
So if I read it like this, you're saying if it's not globally finitely generated, we don't have integrating groupoids?
Yes. Well, I agree with the statement. Yes. Okay. So the proposition is a statement that tells you what are. Well, you can read it like this. It tells you what are the smooth integrals of the singular subalgebroid. Well, you might as well assume that it's projective because otherwise you have no smooth integrals. So this is saying the smooth integrals all arise as follows. So you take the holonomy groupoid. That is a smooth integral. So it's a Lie groupoid with a morphism 2G. There will be with a morphism of Lie groupoids 2G. And any other smooth integral is kind of a cover of this. So has a morphism of Lie groupoids to this, such that the map at the level of the algebroids is just identity. And so this can be viewed as a generalization of the statement of Wolfgang, but if that statement was for widely subalgebroids, this is for a slightly more general, in a slightly more general setting. Okay, so this was the last slide, and so I have to summarize. Well, the content of the talk is I want to address the integration problem. So the singular subalgebroids. I propose a solution that is maybe it's not optimal, maybe it can still be improved, and to show that it's a reasonable solution, I look at some classes of examples, and all the things that you expect to appear as examples do appear as examples, and so it's a good notion, and that's it. Thank you.
Thank you very much. Are there any online questions first? Okay, if not, are there any questions in the room?
So coming back to the last implication, if you look at an example where you have R2 and you look at vector fleets vanishing at the integers, say positive ones with order k and integer k, so it's not finitely generated. So you say that there's no, in your sense, no smooth Lie groupoid integrating it.
Yes.
And do you think one can relax somehow the conditions to get one?
Conditions on what?
On your integration, right? In this example, which may be even due to you, this example, I learned from Camille.
Yeah. No, I don't think you can do anything about it. I mean, if you have, so if you have a Lie groupoid is by definition, the space of errors is by definition a finite dimensional manifold, right? And it has it's Lie groupoid, it's the algebroid, which is by definition or by construction a finite rank vector bundle. and so whatever you do to it, you will not be able to recover a singular foliation such as the one we described, which as a module is not globally finitely generated, but it's only locally finitely generated.
Yeah, you need an infinite rank vector bundle, right? Already.
Yeah, if you're willing to work instead of with finite dimensional manifolds with infinite dimensional manifolds, then yes, then yes, I agree.
Thank you. Okay, are there any more questions? If not, let's thank Mark again.